podcast. This is Mr. White.
And Mr. Sadler.
And today we're going to revisit some old topics, but apply them to roller coasters. And of course, those old topics would include centripetal force and acceleration. We're going to revisit this concept of apparent weight, normal force, weight, and friction. It's all starting to come together, I think. So, Mr. Sadler, help refresh my memory. Centripetal, what does that word mean?
Center seeking.
Center seeking. So, the centripetal force is a center seeking force. And so, centripetal acceleration would have to be, the object would have to be trying to get to the center of an object or a circle of some kind?
Well, it's actually isn't it the force that you feel as you're going around a turn? The center seeking force going around a turn?
Yeah, but people remember, they get that confused with this other physics word, centrifugal.
Right.
Which is actually, I believe it means false force. Because when you're on the roller coaster and the coaster's making a hard right turn, you lean one way or the other.
Push to the left, or your buddy is pushing against you.
Right. And what are you experiencing there?
You're experiencing centripetal acceleration.
Because you're going around the curve.
The car's going around the curve, and you have inertia, so you're being thrown the other direction.
Yeah, you're wanting to go in the direction you were going a moment ago.
Yeah, just like first law.
First law, yeah. Okay. So we have this concept of a center-seeking force, and we're trying to relate that to apparent weight and real weight and normal force. And I can't spell. No one saw that.
We talked about, apparent, just like apparent, right?
Yeah.
Oh, it's weight.
Yeah.
We talked about apparent weight, and we talked about how you feel light and heavy on an elevator. So the same thing must be true on a roller coaster.
Right.
At the bottom of the hill, as you come down very quickly and start heading back up, you must feel heavy at the bottom. And at the top of the hill, where you're thrown out of your seat or lifted out of your seat, you feel light.
And that's true. But we spent a lot of time talking about, okay, well, we're here, and we are here. But we didn't spend any time talking about the loop-the-loop here.
Right.
And the loop-the-loop is actually quite interesting. So let's focus on some different parts of that loop. And if I can try to draw a circle.
Oh, not too bad.
That's not too bad. And so let's talk about, I think, probably the easier section of the loop-the-loop, when you are at the bottom of the loop-the-loop. What kind of forces are acting on you in the loop-the-loop at the bottom?
Well, obviously gravity.
There's some gravitational force, okay. We'll give that a special color. FG, okay.
And then we have the normal force.
The normal force, okay. And I'm going to draw the normal force really big.
Okay.
Why?
Because the normal force should be more than gravity, right?
And so what kind of sensation do I feel?
Heavy.
I feel heavy. So you feel heavy at the bottom of the loop, just like you feel heavy at the bottom of the hill.
Right.
Same basic idea here. And these two forces add up, and they result in which force?
Centripetal.
The centripetal force. So if I were to take the blue arrow plus the red arrow, I would get the black arrow.
Correct.
In this particular case. So the centripetal force is supplied by the track.
Correct.
And it is pointing towards the center of the circle.
Correct.
In the same direction as the normal force, which happens to be perpendicular to the surface.
Correct.
So, very interesting idea.
It's important when we get to the other side, I'll bet.
Probably. So the other side.
But again, the normal force, it's not like we're on the ground. The normal force, the only contact that the coaster has is with the track.
Right. No other physical
Right.
contact.
So when we get to the other side, the normal force has got to be coming from the track again.
Right. So let's start with the easy one. What's the easy one?
Gravity.
Gravity.
Gravity doesn't change just because I'm upside down.
Correct. Okay. And normal force?
Normal force has got to be coming from the track.
So
It's got to be the same direction.
I'm going to draw it like this. So you're telling me that this is the correct response?
Correct.
Uh-huh.
That's the one I think that they don't understand. But if you think about it, the reason that the roller coaster stays on the track is because of that.
Right. So if this track or this normal force were to disappear, the cart wouldn't be able to go forward.
Correct.
Or it wouldn't. It would start to slow down.
If the normal force wasn't there, no, it wouldn't slow down. We'd go spinning off the track.
Oh, right. Right. So there's be nothing there to change the direction.
Correct.
Okay. So does my rule still apply with the centripetal force?
You add the two together?
Yeah.
Absolutely.
Okay, so I hesitated to draw this like so, but I could have just as easily drawn
The two back to back.
the two tip to tail.
Right.
And in this particular case, and maybe I didn't do it justice, we said down here we felt heavy because the normal force was bigger than the gravitational force. So if you were sitting on a scale, the scale would read larger.
Correct.
And so remember, this is, of course, our apparent weight. What about up there?
We're going to feel light.
So I probably drew these arrows at an incorrect length. Really, I should probably draw the weight bigger. By the way, your weight doesn't change. So the weight here and the weight here should be the same.
Correct.
And this normal force is the other that should be shorter. But by the way, when I add them together, I should still get the centripetal force. The centripetal force is still the result of both the gravitational force and the normal force.
Correct.
So I feel light at the top of the loop. So these sensations that you feel, by the way, you feel them coming and you feel them going, because of course, you know, you're coming down and you're coming down, and you're at the. It's not like you're all of a sudden at the bottom. You get that sensation of heavy, and then the heavy goes away, and you become lighter, and then lightest, and then heavier, etc.
Right. So if, someone might be inclined to think that at the bottom here, we're just sitting still there at the bottom, but we've come from somewhere else.
Right. So there's a lot of ways with which we can think about this. If we were to maybe bring this concept of circles into the entire roller coaster track, what you can discover, if you want to discover, is that there are circles everywhere in a roller coaster. So like there's this, obviously a circle in the loop-the-loop. What may be less obvious is, I should probably change colors, is that there's another circle through here. And what this allows for is different radii.
Which means different centripetal acceleration.
Right. And over here, which is going to be harder to see because I've run out of space, there's another circle still, but there's going to be a radius nonetheless. Right?
So basically the roller coaster is a continuum of circles.
Right. And so when these engineers have this in mind, they're thinking about some things. They're thinking about the centripetal acceleration, which is how fast are they going at each of these points, and what is the radius at that point. The speed, is we've talked about endlessly, is dictated by the height, but the acceleration on these circles is dictated by the radius.
Right.
So if we make this R value too small, then the acceleration gets to be too big. Of course, we combine centripetal acceleration with mass to get centripetal force. So we've talked about this in other podcasts. Maybe they haven't seen all those podcasts yet. But in order to be safe, what sort of seems to be the magic number? We want the centripetal acceleration to be less than what?
4 Gs.
4 Gs. And what does that mean exactly?
It means 4 times the force of gravity. So it would be, if you consider gravity about 10, then it would be about 40
meters per second
squared.
So 4 Gs, if we think about that, so you don't want to have a sensation of larger than 4 times your weight. Okay, so this is very convenient for me. I weigh about 180 pounds. So if I were to go into the weight room, 180 pounds is 4 45-pound plates. Okay?
Right.
So that's 1 G. And if you were to stack that on top of me, it wouldn't be very comfortable, but I could deal with it. 2 Gs would be 8 plates. 3 Gs would be 12 plates. 4 Gs would be 16 plates sitting on top of me, and that would become dangerous at that point.
Absolutely.
Now, you're only feeling that 4G for a very brief moment in time, but just to give you some idea. As an astronaut, if I were an astronaut, I would have to be able to sustain 10 Gs. Okay, so that'd be 40 45-pound plates for a very, very brief moment of time. I don't even want to think about that.
I don't want to think about it either.
That would be too much.
One of the podcasts that I did put a link to some of the training that they do.
Right.
I think Air Force training it might be.
Fighter pilots also have to undergo some of this testing.
And it seemed like over and over that if they blacked out, they woke up and they were handed a barf bag because the sensation. So
Wonderful.
I know that fighter pilots actually wear special gear to squeeze their legs to try to keep the blood in their head.
Yeah.
They learn exercises to try to squeeze and keep the blood in their head.
Yeah, because if you're passing out flying a $250 million aircraft, it's not that they're not concerned about you, but they're a little more concerned about their aircraft.
Exactly.
So I believe that covers centripetal force and acceleration, how it relates to the loop-the-loop. On the next podcast, we'll get into some of the mathematical detail of this. So signing off, this is Mr. White.
And Mr. Sadler.